Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody watching us from the future. So my name is Justin Fourny. I'm passionate about data, about databases, and I'm going to take you through the journey of the past, let's say, 20 years of evolution in the database world. Some of you visited the Information Systems for Engineers lecture. Who was there? Quite a few of you. And so that was the prequel. So basically what happened from the 70s all the way to, let's say, the 90s. And now we are going to cover everything that happened more recently. And the idea is that you will be able in your projects, maybe that you will have during your studies, to query data, even if it's large amounts of data and even if it's a big mess. And I'll explain, of course, what it means for data to be in a big mess. It has to do with normal forms. So this is the goal, and we'll see not only how to use these technologies, but also how they are implemented to look a little bit behind the scenes, and we'll learn all of the secrets of this. So to start with, I would like to tell you about scale, because it's all about the scales in which we are now storing and querying data today. So if you take the scale, to give you an example with meters, with length, this is a typical human being. Let's say 1 meter 85. Now, if we zoom out, we have the whole planet. The circumference of the Earth is roughly 40,000 kilometers. It's actually on purpose a round number because this is how the meter was defined long ago. Now, of course, it's defined on the speed of light, but this is the now already kilometer, an extra prefix, and even 40 megameters if you use the prefix for a million. If we continue to zoom out, now we have the solar system, so 150 gigameters separate us from the sun. At that point, kilo, mega, giga, you have heard of all of that, right, in the context of hard disks. Now the distance from the sun to Jupiter would be a terameter, and the distance for the whole solar system, so all the way to let's say, I think it's, I took the heliosphere or something, then it's a petameter. If we continue to zoom out, then we actually realized not so long ago, actually, that we are part of a galaxy that are exactly what we used to call nebulae a long time ago. And now we are at 1,000 hexameters. And if I continue to replace the prefixes, 1 zetameter, and then we have billions and billions of galaxies like this. And if we look at everything we can see, which is basically, there's maybe even more than that, but everything we can see, that would be 138 yottameters. That's not even considering the expansion of the universe, because if you consider that it all expanded, now it would be even further away. So you see all the prefixes that we've been using. And what is actually surprising is that we have enough prefixes to express all of that. We can even measure in a relatively compact written form the size of all the visible universe. And so what I like to say is that when we explore the infinitely big, we actually also have to explore the infinitely small. This is what astrophysicists are actually doing when they look at the conditions of the Big Bang at CERN. And we actually do the same in big data. In fact, you can see physics as the study of the real world, right? So this is the matter and energy. And in data science, we study the data world, but it obeys some of the same rules. And I like to see data a bit like of kind of physics or even chemistry. We have atoms, molecules of data that we assemble. So before I continue, I would like to have you test the quiz that we have. It's a clicker app developed by ETH. I'm just going to ask you what program you're from and see the ratio that studied information system for engineers. This is new, so if you're used to the older version, you can no longer use the mobile app. This one is now deprecated or even obsolete. You need to go instead with your phone or with the computer to eduapp.ethz.ch. They simplified the whole thing. By the way, they communicated, I don't know if you saw it, but they communicated that you even have your ETH card in there. So if you want to, at the Mensa, you can use that app. But anyway, please go there, and then I will test it. Hopefully there's no bug and it all works. There you go. Ah, of course. I told you demo effect. Let's see. Otherwise, I'll just drop it. But it would be a bit sad if we cannot make it work. It was working just before I started the lecture. Maybe we can no longer open all the pages in the background, and now it works. All right. So what is your main background? Normally, you should be able to find it in the app. I'm going to give you a bit of time for you to be able to open it. So now, let's see. All right. So a lot of electrical engineers, computational science and engineering, computer science, data science, I imagine it's the DAS or the CAS, so continuing education. We have statistics students. All right. And others. Do we have physicists? Ah, some of you, theoretical, practical? Theoretical, very good. All right, there's a link actually between quantum physics and relational databases. That's another story. All right, and I have this one too. Have you taken the course Information Systems for Engineers? I'm going to close this one just to see. You can do it on Zoom, by the way. It's both for people on Zoom and in the lecture hall. All right. So I'm going to explain the link between the two lectures, and it's absolutely no problem if you have not taken it, because the two lectures are actually sufficiently decoupled for this to work. So let me now go back to the slides. All right. Okay, so this is how it works. I basically have two lectures, Big Data for Engineers, Information Systems for Engineers. And you are in Big Data for Engineers. You can take Information Systems for Engineers next semester if you want. That's absolutely no problem. And the expectation is that master students in computer science, data science, they're supposed to take big data. And Big Data for Engineers is for all other departments. So this is specifically done for people who do not necessarily have a computer science background. So I'm going to explain everything. You can ask questions, and you know you're not the only one who might not have all the bachelor level knowledge of computer science. So this is specifically made for you from all other departments. All right. So the way that I like to explain the relationship between mathematics, physics, computer science, and data science is like this. Before we had computers very far away, it was all philosophy, right? And then everything emerged from philosophy. And then we could kind of distinguish between mathematics and physics in terms of model logic. So I don't know if you ever heard of model logic. It's basically logic that deals with necessity, possibility, impossibility, and so on, contingency. And so the idea of math, and of course philosophers might have a debate on that, but you can basically do math from your armchair and with a whiteboard, right? You don't need to go out there. You can just think about it and derive a lot of rules and theorems. But in physics, it's different. In physics, you have to go out and experiment, right? You need to figure out, for example, if you launch a ball, that it's a parabolic trajectory and so on. So all of these rules, we obtain them by experiments, right? The universe could have been otherwise. This is what is called contingent. And so we have to experiment. Now, if we fast forward to today, computer science, you can actually do a lot of theoretical things. Many people that's something that computer science students experience. Many people think computer science is about how you make computers work, but in fact, there's a lot of theory too, like the algorithms, the algorithmic complexity, the Turing machine, and so on. So that's a lot that you can also do. There's a lot of computer scientists who only use the computer for LaTeX and for sending emails, right? In data science, you have to get out there. You collect the data and then you analyze the data. It is also contingent because the data might have been otherwise, right? We need to see the data to derive things about the world. And in a way, you can see data science as the physics of CS. And in fact, in CERN, they are doing exactly that. In order to detect the Higgs boson, it's not like they sit in front of their computers live while they have just switched on the LHC, and then suddenly there is a big beep like, yeah, we found the Higgs boson. That's not like that. They just run over and over and over and over and over again the collisions, collected the data, shared them with the community, and then it was a database problem. They queried the data and they figured out that there was a Higgs boson in there. So this is already going in that direction of data science and acting based on the data. We have a lot of wisdom actually from very long ago that numbers are not enough. You need to derive good decisions based on knowledge. And so the key is how to extract information, knowledge, wisdom from all of this data. So now I'm going to take you to start with a short history of databases. You might already have seen that in the other course. I'm going to keep it quick. So what is database prehistory? Well, it's basically everything that is prior to 1970, which is actually not so far back in the past. So very, very long ago, people spoke and sang. This is how you basically communicate knowledge to the next generation. Every time you just remember and then you communicate and by word of mouth, transmit the knowledge. But the problem with that is that you can lose information, you can forget, you can distort information. So with every generation, the information might change and be less reliable. That was actually solved with writing. And with writing, we can encode things that are going to be there for thousands of years. And this is why we typically consider, not for databases, but everything else, that history started with the first tablets, like these clay tablets and everything that is engraved. So this is the Rosetta Stone that was famous in Egyptology. And so we now can access information exactly as it was thousands of years ago. We just need to decrypt it. We haven't decrypted everything, of course. AI accelerates that a little bit. But for what we can decrypt, we see it exactly as it was thousands of years ago. But there's even better than this one. This is just text, right? But there's even better than that. We also found some clay tablets that was in Mesopotamia, where we don't have text, we have relational tables, actual tables. This actually is geometry. It contains the integers, that form the side length of right triangles. So Pythagorean triples, I think it's called. And it's incredible because what that tells us is that relational tables are actually thousands of years old. And this is one of the most intuitive constructs that humans can understand. They even understand it better than scattered plots or pie charts or whatever you can plot the fancy visuals. Tables is one of the most universal means of making data understandable by human beings. Then comes the printing press. Printing allowed us to duplicate data at scale. Millions of same versions of the same book. It led to all the newspapers in the golden age of the printed press. And so that's the duplication. Before that, before printing, the duplication was done by actual people who just needed to do it one by one. So that took a lot of time. Then we had computers. Computers accelerated everything. They allowed us to store more. They allowed us to be faster and faster and faster with the querying of the data. First, it was mechanical, and then came the semiconductors with transistors and so on that made it even smaller and even faster, right? And then we arrive almost to the history of databases, where what we were at in the 60s is that we stored data in a file system, so directories and files. You might know that from your laptop. On the phones or smartphones, maybe it's a bit more hidden, but they also have that. This is what people were doing back then. They would store their data in the files and then write computer codes in order to query the data, right? Then comes database history, because 1970 is the turning point at which a person called Edgar Code had the brilliant idea that because everybody understands tables so well, why don't we completely hide these directories and files from the people and just show them tables with columns and rows? Everybody understands that. And that's what we call data independence, right? Data independence, I say that a lot. Then a bit later, in the 2000s, we had more kinds of ways to store data. We have key-value stores, triple stores, column stores, document stores. I'll show not the triple stores, and the key-value stores, but column stores and document stores we'll study in that lecture, right? So these are the a bit more recent constructs, right? So what is big data? It's a buzzword, because you hear it everywhere, and the problem with buzzwords is that it's very hard to understand what they mean, so I'm going to try to give you a meaning of that. We are going to see a lot of brands. It's not because I'm being paid or anything to advertise anybody, it's just that this is how it happened, right? In the 2000s, it's the companies that actually hit a wall with the data that they needed to store, and so this is why a lot of this technology actually emerged from companies. So you might see here and there a few of these. So when we speak about big data, we like to talk about the 3 V's: volume, variety, and velocity. I'm going to go through each one of them to explain to you what is meant with this. And then the 3 V's, that's how to make it easy to remember. So first, the volume, data volume. It kind of just happened to us. And why did it happen to us? That we have more data just because we can. We have the capacities to store more data, and it just happened. In fact, until a few years ago, many companies were just keeping all the data just in case you need it. It changed a little bit with the data protection laws, because of course you cannot do whatever you want with the data, comes with responsibility. And so, for example, in the EU, in Switzerland, now they have requirements on whether or not they can keep the data. But technically, we actually have the capacity to keep it, and this is why it kept growing and growing and growing for decades. The second reason is that data carries value. Why? Because you can actually act on it. You can deduct some information from it, and then you can act on it. If you consider blockchain or Bitcoin, it actually carries value through the fact that it stores transactions and some ledger with a mutual agreement that it is a source of truth. Then we also have that data is more than the sum of its parts. We'll see, you've already seen that the sum of data, that's actually what we call a join, right? We have different data sets, then we join the data sets, and together you can actually obtain more information than you would have with separate data sets. So there's a lot of value in combining different data sets. Again, whether it's a good thing or not depends on the context. Data protection probably also makes you want to limit that a little bit, but it's the idea, right? Then we have data totality. That is yet another motivation, is that if you are a website that, for example, allows you to search for the cheaper flights or the cheaper hotels, then you want all of them, or as many of them as possible, right? It only makes sense if you have a whole coverage, right? So this is also another reason why we want to store the data. Another example is of database is in Switzerland. You have to register when you live somewhere, and for example, to receive the bill for the TV, I don't know how it's called in English, but the broadcasting fee that you need to pay every year. There is a database with everybody, and it's based on that database that the bills can be sent. So because of that, it happened that it grew, and so we have prefixes. They are all standardized by some international standardization bodies, and they agreed on this. So you might know the first ones, because of you're used in the context of computers, right? Kilo, mega, giga, tera, and maybe peta. I assume you know them. The rest, maybe not. Hexa, zeta, iota. Rona and Queta are actually just a couple of years old. They're actually very recent because we run out of zeros, so we needed to add 2 more of them. I think they needed it for the weight of Jupiter or something, these 2. So that you have to know by heart. How do you remember? If you know a bit of Greek, ancient Greek, I don't know, maybe in today's Greek, it's also maybe similar. Tetra is 4, penta is 5, hexa is 6, and so on and so on. And so you see tera has 4 groups of 3 zeros, penta has 5 groups of 5 zeros, hexa has 6 groups of 3 zeros. So this is how I remember this, right? All right. Now, let me ask you what you think about what big data actually means. So from what quantity of, I just need to learn how to do it now with the new version because there's a few things you can no longer do in the same way as we did before. So from what quantity of data do you consider it to be big? 1 gigabyte, 1 terabyte, 1 petabyte, or 1 exabyte? Right? So a majority says petabytes. I would agree. I think it's the consensus. There's no real or wrong, right? But 1 petabyte is commonly what people would think. Terabytes, it's already interesting for big data because you can already use that kind of technologies, but it fits on a single machine. So you don't necessarily need a data center yet. Petabytes is, you need a data center. Now, it's going to be funny, but petabyte isn't even considered big anymore by some companies. Some companies even add the exabyte scale now. All right, so let me come back. All right, now of course there's, all right. There's a few bugs that prevent me from landing where I was, so I just have to fast forward. Not the best, but just losing a few seconds. Yeah. All right, so what is amazing is that if you look at these prefixes in the context of data with bytes, we have basically gone to Jupiter and even the end of the solar system in just a couple of decades since the inventions of the computers, right? In terms of scales, and this is something really amazing in terms of technological development, right? And it's not even stopping. We continue to reach higher and higher scales for data. Now you might know that computer scientists absolutely love powers of 2. For this reason, when you talk about computer scientists and you tell them it's a kilobyte, they might think 1024 and not 1,000. And that's because 2 to the power of 10 is roughly the same as 10 to the power of 3. But because of that, it was a bit of a mess because not everybody knew anymore if you mean 1,000 or 1,024, and that was standardized too. And in order to standardize the powers of 2, we just gave them other names like Kibi, Maybe, Gibi, and so on. Not a lot of people use that, but you could just know that they exist. And of course, I'm not expecting you to know this by heart, even though some computer scientists might, because they like to learn powers of 2. But you don't need to know this by heart. What I want you to know by heart is this one, right? These prefixes right here. Okay. So that's for volume. Now, variety. This one is simple to understand. It means that even though at the beginning, we consider tables to be the one thing that most humans can understand, we quickly realized, more recently, I would say in the 2000s, maybe even in the 90s a little bit, that there's something else than tables out there. And there are other shapes of data that also make a lot of sense. And other shapes include trees. We're going to see plenty of trees in this lecture, XML, JSON, and so on. Graphs are also graph databases. They're actually quite a buzz at the moment with Neo4j and so on. Then we have cubes. This we cover in information systems for engineers. That's for business analytics, when you need to display fancy sales reports, for example, or do inventory or balance sheets and so on. And then we have, and here I made a bit of an upgrade to the slides because I used to say unstructured and so on. And then I would have the fifth category that would be vectors, when you store collections of vectors. Why? Because now this is establishing itself with large language models like ChatGPT and so on. Internally, we actually have collections of vectors. And now we are building a lot of database systems specializing for storing very large quantities of vectors, highly dimensional, and then computing multiplication, addition, scalar products, and all kinds of things in there. So this is why I'm saying vectors right here. All right, so that's variety, right? And there's going to be a lot of that in big data for engineers. And the last one is velocity. That's the speed at which we are able to access the data. So the thing is, we just keep producing data. It's the logs on the websites. It's the whenever you interact with something or a piece of software. It's the sensors. Even at CERN, we collect the data. I mean, we just keep collecting data as we actually go on with our lives, right? So it's just a real-time byproduct of our activity. But I want to show you why this is actually problematic technologically. In order to do this, I'm going to take three notions: capacity, throughput, and latency. I'm going to quickly explain what it is and why we have a big problem. Capacity is how much data we can store. For example, the size of a hard drive. Throughput is how fast you can transmit the data. How fast can you read it or write it, right? It's the number of bytes per second that you can read. And latency, or one of the meanings of that word, is how much do you need to wait until you receive the first bit of data. Some people say latency for until when you receive the last bit of data, but here I'm taking the first bit of data. So when do you start receiving data? For example, because of the speed of light, or because of there's a mechanical part in the disk, you need to wait until the head that reads is on top of the bits that it wants to read. So there's a bit of latency. And to give you an example, I did a bit of archaeology, computer archaeology, and I found the first ever commercially available hard drive. It's actually almost 70 years now. That had an incredible capacity of 5 megabytes, throughput, 12.5 kilobytes per second, latency, 600 milliseconds, and the dimensions like this, really, really very large. So 1 meter times a meter 70, so almost as high as human beings, and 1.5 of depth. So it's actually very, very large, and now it looks almost ridiculous by today's standards, because now if I zoom in, oh, that's a picture of what's inside. So this is basically one of these where the data is stored. It's a disk. And then that is actually all of the disks on top of each other. And then you have some reading heads that stays somewhere. And then you rotate the disk to bring the bits below the reading head, right? So this is what it's made of. But if we zoom in, then this is what we have today. I even have to zoom in a little bit. This is the largest I found. I upgrade it every semester. Now it seems that we are at 100 terabytes for a disk like this, something like 3.5 inches. 100 terabytes, throughput 500 megabytes per second, latency 0.1 milliseconds, because that's actually an SSD. It's not even mechanical anymore. It's these flash drives, similar to when you have a USB stick, right? So it's amazing what we have today, right? What if we compare this with the former one? So I did that. I run the math. I needed to use Excel. So let me show you directly. And this is what I found out. And there, I don't need to click to show the throughput and latency because they're already there. So this is the factor of improvement. By how many times has it improved? So the capacity, if you divide by volume in order to account for the fact that it's smaller now, so the capacity per unit of volume has increased by 91 billion. 91 billion more. You can store 91 billion more per cubic centimeter. The throughput, the number of bytes you can read per second, a mere 40,000. Almost looks ridiculous in comparison to the capacity, just 40,000. And the latency, so now with SSD, it's a bit better, but it's still less than the rest. It's 6,000, the factor. So if I do some logarithmic thing, then that's what we basically get. The conclusion of that is we are in very big trouble, or at least we were in very big trouble because we found a few solutions, but we are really, really in big trouble. And to show you the intuition of why, instead of a hard drive, let me take a book. So I measure the capacity of a book with the number of words. So let's say 600,000 words. The throughput is how much can a human read per minute? Let's say very roughly 1,000 words per minute, right? That would be the throughput. And then the latency, that's when you need to stand up, go to the shelf and pick the book, right? Or order it from the ETH library and then go get it, right? So this would be the latency there. Now, imagine that today I take one of these books and I do the math. How much time do you need to read the book? Like division by these two. So we say 10 hours. Maybe if it's a Dan Brown novel, a bit shorter than that because you read even faster, but that's kind of reasonable, right, to read a book today. Imagine that we fast forward 2 centuries later, where for some reasons we are able to read much faster and we can also store more with the same factors as what actually happened with the hard drives in the past 70 years. This is what we get. There are so many zeros that I actually need to think. So billion, trillion, quadrillion, 55 quadrillion words in the book and 40 million words per minute, right? It's also faster. But the thing is, to finish that book, one person would now need 2,613 years just to finish the book. That's exactly what has happened with the hard drives. We can store a lot, but we can no longer read them entirely fast enough anymore. So this is what I mean with big trouble. So how do we fix this? We have ways to fix it. One of them is to parallelize. By parallelizing, I'm just basically divided the book into chunks, for example, many chapters, and then I'm distributing the chapters to everybody on the earth, right? I'm giving one chapter to everybody. Then we can finish it in 10 hours, right? But I need to distribute it. This is what we do actually in data centers. We distribute it on plenty of machines. That I'll come back to in the next couple of weeks. It's very important for big data for engineers. That is one of the tricks that we have to solve the problem I've just told you. And we have a second trick to solve the difference between throughput and latency, even though that one is actually not as bad as the first one. And the trick is called batch processing. Batch processing is the idea that you avoid context switches. You probably noticed when you want to study different courses, and if you keep changing every minute the course that you're studying, it's going to be tricky because your brain constantly has to switch, right? So what you do instead is you're going to study for an hour this course and for an hour this other course, but you stick to it for an hour. This is batch processing, right? You avoid the context switches. And this is exactly what we do with data. We try to process it in batches instead of small amounts. And this is one of the tricks to solve this second issue. But I'll come back to that. This is exactly what we'll study in this course, right? So as a summary, big data allows us to store, manage, and analyze data solving this big issue I told you about, the discrepancy between capacity, throughput, and latency, right? We solved that. So why do we do that? Because it has actual applications very, very quickly. CERN is an example I already gave, right? We want to find the Higgs boson and find new particles, and they keep increasing their computing power, right? This is even a bit old, but this is just the slope that it has is absolutely amazing. By the way, if you're interested, we wrote a paper about the use of query languages. In that context, we noticed that they were not using SQL, and we try to investigate why and how we can improve this whole thing with better languages like JSONic that we will study and making it more performance. All right. Another application is trying to build a map of the stars and galaxies. So we have telescopes that are looking at the sky, and we try to store everything we can that we find in that sky. So there's the Sloan Digital Sky Survey that has been going for quite a while, actually. And they have several phases where they scan the sky and they keep increasing the database. And I think there's even more projects going on right now where they also try to build maps like this. So this is amazing because that's actually a lot of data. You can download it, by the way. If you go to the website, well, it will not fit on your laptop, but the data is actually there. Yet another example is the DNA, right? We can also consider the DNA as some sort of data storage. There's even now techniques that allow us to edit it. And there are even people who manage, some of them were at ETH before, to actually store relational data on DNA and execute SQL on DNA. Right? They actually did that. And I'll come back to that in terms of data independence. That's yet another illustration of data independence. Right? So you can also use that instead of a computer as a storage layer. So now coming back to this lecture, data science is very large. I'm going to teach you how to store and manage data at these scales. I'm not going to touch machine learning or AI, but that comes on top of this, right? So these are extra layers. We are going to focus on the database layer. So now we have the TA team. So right here, so I'm going to introduce. We have, I think most of them are here. So we have Zikai. Maybe you can all stand up. The TA team. So we have Zikai with the head TA. We have Ludovica. Right there, we have Alexandre, we have Christopher, we have Cyan, and we have Luca. Right, so maybe a round of applause to welcome them, and they will be hosting you in the exercise sessions and help you whenever you need some help. Zooming and Mélisande, maybe they are here on Zoom. All right, just asking just in case. Okay, thank you very much for being here. And there is also Ethel. Who heard of Ethel? All right, so Ethel is actually a chatbot. She's also a student, just like you. She's learning. She's been trained at ETH, and she's available at ethel.ethz.ch. There is the textbook. She learned the whole textbook of the lecture, and you can ask all the questions that you want there, right? So do not hesitate to use it to give feedback. It's within ETH, so ETH has control over that. I think it's based on OpenAI, but under ETH's control. All right, so don't hesitate to also make use of it. I'm saying it's an AI student and not an AI TA because, as you know, AIs can hallucinate. So this is why you should talk to her with care. But I think it's very useful to sometimes accelerate your learning. Now what we recover, a lot of things. We are going to start next week with object storage and cloud storage. So how can you store data in the clouds, for example, on Amazon S3, Azure Blob Storage. Then we'll look at distributed file systems. How can you replicate the file system on the laptops? I see a few laptops right here. How can you build the same in a data center? We'll look at syntax. Syntax is very important to store data and exchange data. You can download data sets in syntaxes over the internet, JSON, XML, CSV, and so on. We'll look at binary formats that are more efficient. We will look then at models. So for models, we'll look at what is called a wide column stores. It's basically something that kind of is a gigantic relational table, but it comes at a cost that we need to be closer to the physical level, so breaches a little bit data independence. So this is known as HBase. That allows you to basically, you can view it as a two-dimensional storage grid of data, where you can put your XML and JSON files in there. But I'll spend an entire week, maybe even 2 weeks on that. Then we look at data modeling. For tables, it's done in information systems, but here we look at how to model trees and how to validate data with JSON schema, XML schema, and so on. And then probably the most exciting part of the lecture, we'll actually process data. And so the way we'll process data, of course, is in parallel, and we'll look at MapReduce. Who heard of MapReduce? Oh, wow, that used to be a big buzzword back then, like just AI and LLMs and so on. So MapReduce, it's no longer the last generation. So maybe this is why people no longer know the name. But MapReduce was the first generation of systems that were able to parallelize the execution. Who heard of Apache Spark? More of you, right? So Spark would be the newer generation of systems, and there's others. So Spark is more generic and even more convenient to use. And I'll also explain to you how it works. I'll talk a bit about resource management, like how do you optimize the resources in the cluster. And then finally, we'll look on an even higher level at document stores. So the equivalent of relational database like PostgreSQL, but with trees, would be MongoDB. And then at query languages, SQL, you will do a brush up in the next hour and during the week, and it's used in Spark as well. So there's Spark SQL, very similar to SQL. And then we'll see for trees that you need a different query language. Sadly, there are 30 of them because it's not standardized yet. So I introduce you to one of them that I co-designed, JSONic, but you'll see if you learn it, you very easily learn any other. That's really for teaching purposes. All right. Now, what is expected from you is that you attend the weekly lectures here in presence. You can also attend on Zoom if you want. Then you can interact, you can ask questions, and so on. Then you have the exercise session, which are hosted by the TAs. Just not this week. It's starting next week, the first exercise session. So there's nothing this week. You might have, is it this week, Zikai, that people can try out the Docker and then they can reach out?
You can all try it out and post questions to Moodle, and we will come to support you.
Yes, thank you very much. So basically, you should try it out. There's no exercise or anything, but just check if it works on your laptop. And if it doesn't, then you have a lot of time to fix it with the help of the TAs, and then you'll be able to use it with the exercises. Very good. So I'm repeating so that everybody hears on Zoom. There's an exercise 0 so that you can try it out, right? So this was built by the TAs to help you, right? Thank you very much. Then you're supposed to read. There's a lot of books and papers that are expected to be read and contain material. And then there's the written exam that grants you the 6 credits if you pass it, right? And there is bonus points. This is actually quite popular. Every week we are going to ask you 2 quizzes with a few questions in there. Every quiz gives you 0.01 points, and they will be added to your final grade before the rounding, and then we round. So this is an opportunity for you to enhance your exam grades by learning throughout the semester. The goal of it is really to push you to learn during the semester. And this is actually quite useful. Most people actually try the quizzes. Why do we want that? It's because of knowledge retention. If you study during the semester, then you will remember this for years. If you only study ahead of the exam, then yes, you will pass. You might pass. You will get the degree and so on. But if you forget everything after that, then as a teacher, I failed, right? So the goal is that you return that in the long term. So this is one of the goals of the bonus points. All right, so you solve them. There's 25 of them. You get 0.n to the exam grade. If you get all 25 of them, it's a guaranteed increase of 0.25, except if you already have 6, of course. And the rest is basically depending on the rounding. But the more quizzes, the higher the likelihoods that your grade will increase. Yes?
Yes, Angelica asked on Zoom, when will the quiz take place during the exercise, or we can do it anytime in the week? I guess I can answer that. The quiz is posted on Moodle, and usually we open at 3 of the on the same day of the lecture to next week, so that can be done at any time. Yeah.
Thank you. Then we have a textbook that was by popular demand a few years ago. So the entire material of the lecture is in there, and you can read it during the semester. It's more or less similar to what is on the slides, but some people like to have a reading like that, right? You have printed copies on Amazon, but if you want the latest with all the typos fixed and so on, then you should go to this address and you can download the PDF, right, for free. And I regularly update the printed copy, but really the preferred place is this place and download the PDF to be sure you have the latest. If you spot errors, let me know. I fix them, and I keep track of the errors in a log at the end of the book. Okay. Then you have Docker, as was explained by Zikai. It's basically some environment that magically makes things work on your laptop independently of Linux, macOS, or Windows. And so what we provide you is a Docker like this that contains PostgreSQL, that contains Spark, that contains like many of the technologies. It is supposed to just work. I'm saying supposed because I know it will not work for everybody. This is just how life is. And so for those of you for whom it will not work, then we will help you. The likely answer is, have you tried to switch it off and on again? Which basically essentially means, have you tried to delete the images, volumes, and containers and to start it all over again? Very often that actually does the trick. Sometimes reinstalling the Docker desktop app works. Make sure you have Docker desktop installed, and otherwise, then the TAs will assist you. All right. In some of the weeks, you might get a different Docker, but for most of the weeks, it's going to be what we call the exam Docker because it also contains some past exam data sets and notebooks. All right. That I already said, and yes, we have a chat instance. I'm going to start inviting people. Please all go to chat.ethz.ch if you haven't already and log in as a student in there with your ETH password. And then I'll add you to the lecture chat room on it's an element server. You can interact in that way with the TAs or even with each other. You can send memes. I know that place has been popular for also exchanging database-related memes. So yeah, and then you have the Moodle, of course, in here with all the material. And I think the TAs prefer the forum as the one place where you're guaranteed to get an answer within a couple of days. This would be the forum on that place. Of course, you can also use the element chat, but if you are not getting an answer there, then try the forum over there. All right. So we are going to take a break now. I had 3 more minutes, but just because I wanted to wrap it up. So we'll take 15 minutes, meaning that we start again at 18 past 9. And what I'll do in the next hour is a SQL brush up. I'm going to summarize in 1 hour all the 14 weeks of information systems for engineers. All right, so don't be scared. Come back in 15 minutes. Thank you.